Hi everyone. In this video, we will discuss how we improve the performance of our loan approval classifier, how we access the refine is fit, and how we would do next if we had more time to and resources. First, we will discuss how we improve the classifier performance. Our training dataset contains 36,000 observations, and the target variable loan status is imbalanced. Approximately 78% of browsers are non-defaulters, and 22% are defaulters. Because of this imbalance, accuracy is not an appropriate metric. A model that predict all loans are non-default would achieve high accuracy but would fail to identify risk borrowers. Therefore, we focus on F1 score, which balance precision and recall. To improve prediction quality, we applied feature engineering techniques. First, we transformed categorical variables such as education level, home ownership, loan intent, and gender using one-hot encoding. This prevents the model from assuming false ordinal relationships and allow both linear and tree-based model to properly interpret categorical difference. Second, we engineered financial ratio feature that better capture browser risk. These include the loan to income ratio, the debt to income ratio, and length of um, credit history relative to age. These ratios are more informative and raw values. For example, 20,000 loan post very different risk depending on whether browser earning 30,000 or 200,000 by incorporating ratios. We improve the model's ability to detect financial stress. Next, we compared three different models: logistic regression, random forest, and light GBM. Logistic regression reserve our baseline. After threshold turning, its F1 score was approximately between 0.72 and 0.74. This strength include interpretability and stability. The coefficient allowed us to understand feature influence, which is important to regulated industries like finance. However, a logistic regression assumes a linear decision boundary and cannot easily capture a complex interaction between variables. Random forest improved performance. Achieve an F1 score around 0.82. It captured nonlinear relationship and reduced variance by averaging multiple trees. However, it less interpret and more computationally expensive and than logistic regression. LightGBM divide the best performance with cross-validated F1 around 0.84. It efficiently captures nonlinear interactions, includes built-in regulationized and performs very well on structured tabular data. The trade-off of reduces interpretability and increased turning complexity. From a business perspective, Light GBM improved the best balance between detecting default and minimizing unnecessary loan rejections. Because the dataset is imbalanced, we expect address class imbalance into two ways. First, we use class weight. By setting class weight to balance, the model penalized misclassification of missionary class more heavily. This helps improve record for default cases without artificially altering the data distribution. Second, we turn to decision threshold. Instead of using default 0.5 probability cutoff, we search across threshold to find the value that maximize the F1 score. For light GBM, the optimal threshold was around 0.59. The threshold turning is particularly important in loan approval setting. A false negative means approving a risk borrower, resulting in direct financial loss. A false positive means reject a safe browser, which result in opportunity cost and reduce customer satisfaction. By adjusting the threshold, we can align the model's behavior with the organization's risk tolerance. We also perform hyperparameter tuning, particular for light GBM. We adjust the number of trees, the learning rate, the number of leaves, and the subsampling ratio. Compared to result setting, using improve the F1 score and reduce overfitting. Lower learning rates combined with more trees allow the model to learning more gradually and generalize better. And next is my group mate will explain the rest of the our models.
Okay, for the next we discussed how we assessed and improved the model fit. Instead of using a simple train test split, we implemented a five-fold three-phase cross-validation. Uh, Stratification ensures that each fold preserves the original class distribution. This reduces variance in performance estimates, producing more stable, reliable evaluation results. Performance was consistent across folds, indicating that the model generalized well. We also examined the learning behavior. The logistic regression showed the signs of underfitting suggestion higher bias. Random forest showed slight overfitting, while the training performance exceeded validation performance. Light GBM demonstrated the most balanced performance between training and validation sets. To interpret trade-off, we analyze the confusion matrix. In the context of loan approval, the cost of false negatives is typically higher than the cost of false positives. Missing a defaulted borrower results in financial loss. Rejecting a safe borrower results in lost revenue. So by optimizing F1 score and adjusting the threshold, we balance these two risks. We also examined the precision recall curve because the dataset is imbalanced. Precision recall curves are more informative than ROC curves. Light GBM maintained a strong precision at reasonable recall levels, demonstrating effective separation between risky and safe borrowers. Finally, if we had more time and resources, we would pursue several improvements. First, we would incorporate external data sources. This may include the credit bureau data, macroeconomic indicators such as unemployment rate and inflation, and some historical repayment behavior. Defaults are influenced by broader economic cycles, and incorporating macroeconomic sizing signals would likely improve the model robustness, uh, especially during the downturns. Second, we will design a production monitoring framework. This would include continuous tracking of F1 score, precision, and recall over time. We would monitor data drift by examining changes in future distributions using the metrics such as the population stability index. So if the performance uh, degrees or significant drift is detected, we would trigger retreating. We would also periodically reliable the decision threshold to align with the evolving business risk tolerance. So in summary, we improve the classifier performance through the feature engineering class imbalance handling, threshold tuning, and the hyper meta optimization. We compared the logistic regression, random forest, and the light GBM and found that the light GBM achieved the highest F1 score and the best business trade-off. We use the satisfied cross-validation for stable evaluation and analyze the confusion matrix and the precision recall curves to understand partial implications. So our goal was not only to maximize the metrics, but to build a model that aligns with the real-world financial risk management and the long-term development stability. So thank you guys for the listening.